So welcome everybody. Thank you, Peter, for the introduction and also the opportunity to introduce Airborne Wind Energy to this community. I will speak about the R&D status and the outstanding challenges to actually lay the foundation for our two industry contributors later. Quick thing about myself. To introduce myself, I'm an associate professor at Delft University of Technology. I have co-founded Kitebauer BV, which is a spin-off of Delft University. We are looking at flexible wing airborne wind energy systems, and we founded this company in 2016. But I'm not actively involved and have to teach students. And the nice thing is the interaction between aerospace students and our company. A lot of students, of course, go to the industry later, so we are actually educating the workforce of the future. I have coordinated two major Horizon 2020 projects. The one is called AWESCO, that was a doctoral training network with 16 PhD researchers at 12 different partners across Europe. And the other one is REACH, which was a fast track to innovation project, which we used to actually spin off the startup. I will be responsible for 4 PhD researchers in a Dutch national project, NEON, that will start this year. And as Jaap mentioned, I am always co-organizing the Airborne Wind Energy Conference, and I'm doing this since 2015, did the one in 17 and also in 19. You can guess that will be 2021. Where that will be, we have not decided yet, but it will for sure be a very interesting event. And I've co-edited these two textbooks. If you want to know more about what I'll talk about now, you can look at these books. They are also online available. Together, I think 1,200 pages, condensed theory in 50 contributed chapters. So I did not write these books, I edited them. But the nice thing is, most of the companies contributed to these volumes on their specific concepts, mixed together with a theoretical preparation of the material. So this is really something I can recommend. In my talk, I will speak about the fundamental working principles, quick introduction, the classification of the concepts, because we will see there are many. I will present a few implemented technology demonstrators, and Jaap and Lode will later follow up on that with their own concepts individually. I will then speak about the challenges of development and research. And you can imagine there are many challenges that we need to solve. Not only technical, also societal challenges and regulatory challenges. And if there is time, a bit look back how this sector developed. I think it's interesting for the people also from wave energy or floating wind. There are similarities. The fundamental concepts. They were introduced in 1980 by an American engineer, Miles Lloyd, and he proposed to take then commercial aircraft, put it on a tether, and fly it in circles and have turbines on this plane to actually convert energy, wind energy into electricity, and then conduct it down here, the tether to the ground. This idea was triggered by the energy crisis in the 70s, and this, let's say, the aim to find other means to produce energy not from oil. At that time, of course, also wind energy was slowly emerging, so that was a very creative phase. And next to that concept, which he called drag power, and I just explained how that works, he also proposed a second concept, where you fly the wing in crosswind patterns, can be circles or figure of eights, and you pull the tether from a drum that's here on the ground. It didn't even specify drum. Basically, you transport mechanical energy to the ground. And of course, the tether reels out, as you can see. And this type of concept will require a cycle. So you need a reel out phase and a reel in phase. These were the two fundamental concepts. He presented them in theory, derived all the formulas for that, and we are still using these today. Of course, refined, because he made quite a lot of assumptions, was very optimistic, as you will see in the next block. But still, the basic message holds. We have here on the left side what I call the regular kite. And on the right-hand side, the crosswind kite. So these are the two concepts that you saw on the slide before. In his theory, he did not distinguish between them. And this is a regular kite that's not flying crosswind, but just reeling out statically. And you see here from this power harvesting factor, which I define here, you can almost not read, you will see here that goes from 0 to 0.4, and for the crosswind kite it goes from 0 to 140 for the same sequence of lift to drag ratios. So you see that with the crosswind principle you can produce a lot more power. Of course, crosswind is also used by wind turbines. Let's not forget that the wind turbine also produces energy in crosswind motion. So the same principle holds here. But the distinguishing element for airborne wind is that we can go higher, that we have much less consumption of material. So this is our tower. You can imagine a lot cheaper than building a steel or a wood or a concrete tower. The generator is on the ground rather than being up in the air. We can adjust this harvesting concept dynamically to the wind resource. So we can make use of the fact that the tether can go out higher, or we can fly lower. Higher altitude wind, I mentioned. And we have an increased mobility. This is functioning very erratically. And on the downside, of course,
otherwise
we'll check the battery, or pressing this, but
it's the trigger. It's this one.
Ah, it's on the back.
Yeah,
okay.
Yeah, it's on the back. Sorry, you have to do pang pang pang.
Yeah. Yes. Okay. On the downside, this is much more complex than a wind turbine. So we have to constantly fly. We have removed almost all the constraints from this harvesting system, except for the tension tether. But in all other degrees of freedom, and there are infinitely many, this thing can move. So we have to have perfect control of this device. And this is also one of the key challenges, let's say. I will call them bottlenecks, but it's one of the key challenges of the technology, to have a reliable and robust operation. And this is the phase where all the companies are currently in, showing that and scaling up at the same time. Also, we depend on high performance materials. Everybody uses plastic fibers, high performance plastic, like Dyneema. It must be lightweight, as you can imagine. It should not be too thick, otherwise we have a lot of aerodynamic drag. And it should also be durable, resisting dynamic bending cycles. And this is also a key challenge for all technology. And of course we need to revise the current regulatory framework because we can penetrate in the airspace of aircraft. There must be a solution. We are working on this in our European Industry Association, Airborne Wind Europe. to actually work out a frame. So, coming to the technology demonstrators, I put down here only 10 representative projects, but there are more. There are about 40, 50 different implementations worldwide. There is the kite, the flexible wing. You have here 3 different concepts. This is our own kite that we use in Delft. This is a 25 square meter specimen that we use since 2011, 12. That's the kite of sky sails. The difference between these is, this is a ram air wing. It's actually it's a mattress that is pressurized by the incoming airflow. There are small openings here on the leading edge that pressurizes the wing itself. Same concept that paragliders use. Whereas in Delft we use the leading edge inflatable wing. Kite surfers will know exactly the difference. This has a tubular frame here in black with a leading edge and then these spars and a canopy in between. And here we have a similar concept, ram air wing from KPS. Then we have also rigid wing systems, these ones here. A V-shaped swept wing of Enerkite. Then here this glider concept of Ampix Power, kite mill here with the VTOL launch and landing system. So VTOL means vertical takeoff and landing. It's basically a hybrid of a quadcopter and a glider aircraft. I say glider aircraft, it's not exactly right. These are aircraft with very high lift capability that can carry 10 times more than their own weight, say very roughly said. So this is not, these constructions are not comparable to glider aircraft, but they look like gliders. Then we have TwinTech, also a VTOL concept. And we have Skypull here, the Swiss company, which also uses VTOL with a box-shaped wing. Then we have Windswept, that looks mostly like a wind turbine. It's basically an array of rotors that is lifted by a lifter kite that you don't see here, and under an angle of elevation to the incoming airflow and rotating. It's quite an interesting concept, and e-wind solutions in the US. So many different concepts, which is why we try to classify this in some way. And this is the latest classification that I made for a journal paper here in Renewable and Sustainable Energy Reviews by, I think, 30 or 40 authors all over Europe. It was part of an EU workshop at Innsbruck a few years ago. So we start here with the Airborne Wind Energy System, and then we distinguish between a fixed, the place where the energy generation takes place, can be either a fixed ground station on the ground or a moving ground station on the ground. Imagine a cart that is pulled around on a rail track, for example. Or the energy generation can be on the flying device in the air. And you see already that here that the second criterion is the flight operation itself, crosswind, tether aligned, or let's say non-crosswind, you could also say, or rotational. Depending on this combination, you get a specific concept. You see that most of the concepts that are implemented use a fixed ground station with the kite flying in crosswind. We will also look at that in the following. The second class of concept that we will look at is the energy generation on the flying device and the device flying crosswind. And this is, for example, here the Makani concept. It's a very famous one, famous because they have the biggest system in the world, 600 kilowatt, and flying, already offshore, floating, so a nice combination for you guys. If you want to know more about these fundamental aspects of technology, I'd like to point you to this website here, wesco.eu. This is the website of our doctoral training network, where I posted a very nice introductory article about airborne wind that goes through the fundamental concepts, the basic formulas, the math, introduces all the main players, and also looks a bit at the historical aspects. It's a bit like the blueprint for this presentation. So if you want to have that in writing, go to that website. We will look at these concepts now in the following. I will give a brief introduction. I will not spend time on Ampex and not on Untitled, because you will do that yourself. So first, let's start with Makani. Makani was founded in 2005 or 6 in California, San Francisco. They had this small-scale system here in operation for many years. It's a wing, rudder, an elevator, and 4 onboard wind turbines. They were able to launch this kite 90-degree rotated and land in the same way like a quadcopter, while harvesting energy with crosswind motion using these onboard turbines here for energy generation. Combine that with the conducting feather. In 2017, they had been bought by Google already by then. They made a large scaling step from 30 kilowatt to 600 kilowatt. They developed the so-called M600. This is an impressive wing of 30-meter wingspan with 8 onboard turbines. You can imagine that the funding of Google was required to pull this off. I mean, they hired an entire team of engineers. They developed an electric aircraft, probably the biggest or one of the biggest drones that is flying, with a specific characteristic to be used for airborne wind energy generation. As I mentioned, with a quite robust wing that is not deforming under the extreme, too much under the extreme load that the crosswind motion will generate. They moved then, after testing in the Californian desert, they moved to Hawaii, where they got, were integrated into the network with the utility. They flew there for 1 or 1.5 years before making the next step. And you've probably heard this in Norway, 2019 in late summer. They built a floating spar buoy, connected the M600 to this. So this top setup is exactly what they had been developed themselves already in California, tested it in Hawaii. And the addition was this floater. With the money of Shell, who stepped in as an investor into that venture, they wanted to demonstrate the operation of this thing. Here you see how it's been pulled up into the sea. This is the platform where the entire control center was placed with the engineers to supervise the tests. Here just before launch. Then here you see the liftoff. This is the critical moment, because you know that this spar moves. Once the aircraft is in the air, it's also moving, so you have 2 moving systems. And landing, you can imagine, is a major challenge, because you need to take into account the dynamics of both systems to get a safe coupling back of the device. Here you see the M600 in harvesting mode. You see how much it pulls. The whole buoy is tilted to the side. And this is a view into the control center. This is just before in the harbor. You see the size of these onboard turbines. And this is all custom developed as far as I remember, there are very few parts that they could just take off the shelf. They had to develop everything, do the component test of everything, develop the entire production chain for these devices. That's the Makani team. 2019, the sub-team in Norway, when they just performed the test. And now I have a movie. I'm not sure if I can get it to work. I can try it. It's a very impressive movie. Oh, you don't see it. It's funny. See it here.
Yes, it's gone.
Okay. Can you see what I mentioned? I think there is even some audio. It's probably more noisy than so lift-off phase. And you see it's also important to have the tether always under tension, because when there is too much sag, you can get quite uncontrolled reaction forces when you hit into the constraint. And they showed this movie for the first time at the conference. Our Airborne Wind Energy conference is also a nice pacemaker for the development teams to have something ready by then. So everybody wants to show the current development status. And I mean, I know how difficult it is to fly with a wing with a few meters wingspan, but this is something which is beyond my imagination. To fly a 30-meter wingspan wing with 600 kilowatt onboard power. I'm not sure, by the way, what the next steps of Makani are. They are very quiet about this. I imagine that they now try to make it more robust, improve, and go into market. So for the offshore, this is certainly a viable solution. Onshore, I heard, is not possible. For one, for the safety issues. For the other one, of course, it's loud. You have these big turbines that spin at very high RPM. The flight speed is 90 meters per second or something like that. So you can imagine what kind of acoustic emissions the system will have. Switch back to the presentation. And I'm again at the start. Interesting. Okay, we continue with Ampix. I have a few slides just to give you a place in the whole system. Ampix started with this AP2, a 50 kilowatt demonstrator that you see flying here on the Nordost boulder. That's northeast of Amsterdam. This is the next step that they are currently preparing, and I'm sure Jan will tell you all about it. It's a dual fuselage, I think also a bit beyond 30-meter wingspan, and it uses the traction force. It transfers the traction force, the pulling force to the ground. And here you see a test setup where they tested launching and landing from an offshore platform. I mentioned this also because my master's student did the dynamic system analysis at Ampix. It was a very interesting subject. They had to model the motion of this platform with the usual simulation tools that you have, and at the same time has a flight simulator and try to get a controlled landing. And I think a lot of the requirements that come from that research actually made it also somehow into the design, because shock absorption and enough clearance for the landing, this is one thing. What he did not design, but Ampix put a lot of weight on, is the braking system, the the runway is extremely short. It's hard to imagine even how that should work, but this plane has to land on the platform and has to be decelerated at a very short distance. Another challenge for sure. Here you see this landing gear, and of course it needs to be retractable, because during harvesting you don't want any additional aerodynamic drag. The theory of Lloyd says, and common understanding, that L over D should be as high as possible. You can see also the tether attachment. This is the wing and fuselage in The Hague. I think it was last summer. A motor test stand. Here a detail of the landing gear component. The setup of the molds for the wing. And that's the outlook. So this was the AP2. We have here the AP3 currently developing. They have also a team that works on the AP4. That's going to be several megawatt power. So this is, I understand, the ultimate goal where they want to go to. And this is a nice illustration from one of the books. Probably AP4, yeah, next to a wind turbine of the same power output. You see the difference in material use and size. There is no tower. Generator is on the ground. It's only a part of the total blade length that is actually used for harvesting. I missed to explain that. For airborne wind, it's really the basic idea is take the outer part of the wing of the blade that moves fastest of a wind turbine, remove all the rest of the turbine, put this outer section on a tether and fly it in the same pattern. That's the material saving principle behind that. And you see it nicely visualized here. Then another startup, Enerkite, to nicely go through all European countries. Here you see a ram air wing that they used still in 2012. They moved to a V-shaped wing for durability reasons. Here you see the wing frame in the lab in Berlin. Then the question was, how do we get this into the air? You saw Ampix has a linear horizontal liftoff and landing. Enerkite goes for a rotational variant of that concept. For this, they retrofitted this rotational mast to their original ground station. The idea is to whirl the wing around and then actually decouple it from the masthead and fly off into production mode. This canard wing here was only added for stability reasons during testing, so normally that is not there. This is the team and their original ground station, and I have here also a movie. You see how it works, the rotation of the system. It took them a long time to actually do this rotation and then decouple the wing more and more. I'm not sure if they are already flying in free flight, but I do know that they have achieved already decoupling to several meter distance, wing to masthead. You can imagine also the forces in that system are immense. I'm impressed that they are sending there.
Yeah.
Okay, we continue. Then we have also Switzerland actively involved with the company TwingTech. TwingTech is a spin-off of the EMPA, the Swiss Research Center for Materials, based in the vicinity of Zurich. Very nice test environment here. This is the current concept. It's a drone with 3 VTOL subcomponents. Here on the launch pad, it's a beautifully manufactured prototype, I have to admit. And here you see the megawatt side, the comparison of a wind turbine with the airborne wind energy system on the kilowatt scale, but then in real. This is a wind turbine of the same power output as the twin-tech airborne wind energy system. They produce the same, and you see with much less material. Now the challenge is to get the operational hours into that system that this wind turbine can achieve. This is where engineers are currently busy with. Now I come to Delft, the Netherlands, and I first want to look at our academic demonstrator. We were one of the first research groups to have such a thing in service for 6 years, from 2009 until 2015. We operated this system here with almost 100 test flights, if not more, gathering a lot of data that was used to build theory, to validate models, and so on, and to also spin off companies. Our setup is a wing and a kite control unit. The tether runs down to the ground station where we have a drum and a generator module. This kite control unit here is where the intelligence sits. It's a cable robot that steers the wing and also powers and depowers the wing. So it can implement the path following control, as well as the pitching of the wing to decrease the force when we reel in for the pumping cycle. I'll come to that later. In this specific system, you see also a pitot tube here for measurement. Maybe this is one characteristic of that system. We have 83 sensors all over the system here. 83, measuring everything from temperatures, velocities, voltages, on the wing, control unit, in the bridle system, on the ground station. And all of these flights were recorded. I will actually publish this in a few weeks in open access. The data set from 2011 until 2015 with 53 flights of these 83 values that can still be used by research groups or companies to improve their modeling capability. So this is what I just explained. Just here a visual plot. We also developed a launch mast to launch the kite from an upside down position, because the question is, how do you get this kite into the air and land it again and do that in a repeatable way without human interaction? One of the ideas was to have this launch mast. I will show you a movie how that looks like. That was still during the academic research time. These were the kites that we used. So that was the first kite, a 25 square meter wing. Then we switched to a commercial surf kite, a Genetrix Hydra, to test a shorter bridle system for the upside down launch. And we then scaled this up into a custom development, this V3 kite with a 9 from here to the control pod that would be here somewhere, was just 9 meters, so you could put it upside down under this diagonal mast. And that we tested here in this setup. Yeah. So here you see how it works. This mast was built by, actually designed by a student of mine. Now we switch to the onboard camera. We look down the tether to the mast, and then we go into this crosswind motion. And now we switch view again to the KCU, Kite Control Unit camera, looking into the wing. You see here the steering tapes and the power and depower tape, just to get a bit an idea how it works. Can't go too much into detail. This is the pumping cycle that we implement. That is also used by Ampix Power, and also by Kiteno. So we have this figure of 8 maneuvers to pull the cable from the ground station. Then we transition into a reel-in phase where we depower the wing, or I think the rigid wing concepts, they use the tailplane to do that. We use the control unit to do that. And then reel in the tether to then transition again to the next reel out phase. So this is what we call a pump cycle, a pumping cycle. It's like a combustion engine only using tension. The frequency or the period is about 1 minute 30 seconds of such a pumping cycle, just that you get an idea. So it's a rather low frequency process, this pumping of wind energy to the ground. And this is how it looks in terms of data. This is the instantaneous pulling power. You see here the pulling phase or the reel out phase. Then we go into the reel in phase. This is production, this is consumption. This is a test from 2012, so very early, at 6 meters per second. You see here the average power that we produce. It's about 12, 13 kilowatt per cycle. This is also the operation at the nominal power, 6 meters per second. Here, you see that? This is the power curve of our system. You will probably ask yourself, why is it going down here? A wind turbine normally flattens out. This decrease here is simply a result of our kite system not being able to depower sufficiently enough for the higher wind speed. So we need too much energy to bring the kite back in. So this is one area of research that we are involved to flatten this out, to not lose as much energy. And I'm sure that the rigid wing concepts are better here because they can actively steer towards the ground station. Now I switch to our company here in 2017. The aim of the startup was to actually produce 100 kilowatt. So we went from 20 kilowatt reel out power to 100 kilowatt average production power that came with an enlargement of the kite. Here you see a 40 square meter kite flying in Falkenberg. Below the altitude of the aircraft. Our test site in Falkenberg is next to Leiden. It's exactly in the flight corridor of Schiphol International Airport. It was not a problem to get a flight permit as long as we don't go above 500 meters. So it's a zoned area, and that's one approach you can go. You have a zone which you reserve for your harvesting, and above that zone you can have aircraft. This is the ground station that they built in 2016. Has quite a massive drum. Can have, I think, 600 meters or more tether spooled on. It's transportable still, so it fits on into a container, or it is a container actually. And this was a test in 2018 with the Dutch military, I think, because they were interested in that system. And this is a picture from operation. And here the same picture during night. So we put a camera, a light on the kite and made a long-term exposure. And it's impressive to me, at least, how perfect the flight, the trajectory tracking algorithm works. Very robust, also against fluctuations of the wind field. This is the envisioned zoning concept for a whole kite park. So multiple ground stations and kites arranged such that they don't interfere with each other. It's a proposal of a paper that we published a month ago about safety and reliability. So this is just a picture to show the kite control unit here. So this is what hangs below the kite. And this is an airborne wind turbine that's attached to this cable robot to harvest the energy that this unit needs during flight. Because we don't want to have electrical cables running through the tether. This is a no-go for us simply because the continuous dynamic bending of the tether when it spools on the drum would destroy such a combination of high-performance plastic and conductor immediately. So that's why we have an onboard turbine. The company decided to ramp up in numbers, so they built 10 of these kite systems last year, simply to try out a kite farm concept at Falkenberg, where we have now 2 systems. They had also a second ground station built. Here you see this setup from, I think, June last year. This is a 25 square meter wing, a 40 square meter wing, and a 60 square meter wing. So it's rather easy to scale up because these are flexible wings. They don't cost a lot. We see them, or the company sees them more as a disposable than an aircraft. This is the 100 square meter wing. You see how large that is. Here in the background you see the ground station. And this is the team of kite power in front of one of their kites. Maybe what I forgot to say is for these large wings, they do not use a launch setup like a mast. The idea was to quickly go to market, find a niche market where you don't need a fully automatic launch and landing, where you can have some manual involvement still. So what they do is they put the wing on the back, like it's standing here. It's clamped to the ground with mechanical clamps. And on launch, when the tether is pulled in, these clamps release and the wing lifts off into the air. That setup works very well in the meantime. It's fully automatic in the sense that there are no people involved at the kite during launch, so that's safe. The only time people are involved is when the kite lands. It needs to be brought back to the launch spot and set up in that way. The idea is to automate that further in the future, but first go to market. This is one concept of Kite Power, our spin-off. They want to be the first in the market to sell systems to these niche applications, for example, military or islands, or customers that are okay with a not fully automatic system setup where people can be involved. Here I summarize what they have achieved in terms of numbers. As a co-founder, I'm also an advocate of our spin-off, obviously. From 2016 to 2019, you see the actual flight days per quarter of the year. That's the purple color here. And the cumulative flight days. What you see here, this dashed line, is full operation every day per month. So this is like, what is it, 90 days per quarter. If we would be here with these purple bars, it would be perfect, because that would mean we fly every day continuously. You see that we are not there yet, although we have a slight increase. And the fact is simply, an airborne wind energy system is complex. We have a short development time. There is always something that can go wrong, although you have redundancy in the system, you tested the software. When you fly in real, something will happen that you did not expect. And this is exactly the reason. So there are weaklings that break at too low load, or a software bug that was not realized or caught during development. These lead to shorter test periods. And also the fact that we have limited human resources. During last year, Kite Power set up 3 different operational teams that could cyclically rotate, simply to have enough manpower on the field to realize operation every day. But still, that was not enough. Now I want to quickly look at the development as an industry and check the time.
30 minutes.
Okay.
Perhaps some 5 minutes questions.
Yeah. You see, we are here in the year 2000. What I'm missing here is the scale. So this goes from 0 to 70 here, 70 institutions. So these were 3, and here we are at 60. You see that in 2005-06, we passed the threshold of 10 actively involved institutions in airborne wind energy, and then it really took off. So this is the time of the early founders, and then you have a lot of followers here that set up business after 2010. And of course, still, we have more and more companies and research groups being involved. This is the global landscape. And what's interesting here is Makani. You see here in San Francisco. Europe has a very diverse ecosystem of companies and academic research groups. Almost 50-50. And that is a reason, that is a consequence of EU funding that had started in 2010-11, very strategically, wisely invested into this diverse ecosystem of academia and startup companies. And the result is that we have a powerful industrial academic complex now, where we solve together a lot of the problems. And our doctoral training network was only one of these joint ventures between academia and industry. To map out the challenges that I mentioned these already, reliability and safety. None of the projects has yet proven more than a few days of operation. I'm not sure if there is one with more than 1 day actually. Operation in kite parks, combining these airborne wind energy systems will be another step. Durability of materials and regulations. And that's one. Now I'm looking at the research fields, and one of these fields is how does the wind resource look like when we go higher? You see, this is where wind turbines are, but we might operate here up to several kilometers altitude, not in the next years, but maybe in the longer perspective of airborne wind. This is a zoom up to 2 kilometers. Here you see the wind turbines up to 200 meters. This is where current kite systems operate around 500 meter altitude. And we need to expand our knowledge of the wind resources above common wind turbine heights. We did that in resource studies. I think I don't have the time to really go into this, but there are some interesting papers out there that you can read, all open access, by the way. But the key message is, what I show here is, we can adjust the operational altitude of the system to the wind resource to always have the optimal point. Because when the wind is too strong, you saw from the power curve, then we lose again energy. So we fly a little bit lower where the wind is not so strong, and in this way we can maximize the output of the system. The key takeaway is airborne wind energy will very likely lead to a higher capacity factor. So we can better use the systems that are out there for energy production compared to wind turbines. Launching and landing is a key challenge, obviously. This is research that we did on our V3 kite for the aerodynamics. Here is just a bit of how the kite looks like from the side and from the front. And as I said, we have more than 80 sensors on the wing and the rest of the system. And one of them is a pitot tube, which we use to do aerodynamic characterization. You see here the result of a student research project with CFD of the wing, and this is the identified lift coefficient, so still see some differences, but CFD is an ideal setup. This is a real wing flying with falls and deformation during steering, so it's expected that the lift is lower, and also the drag is higher than the computed drag for the same reasons. So we try to get closer and closer by having more accurate aerodynamic models. Wind tunnel testing is another option, obviously. Or doing high fidelity simulations. This is a ram air wing where we tested, or where we simulated fluid structure interaction. So we have an internal pressure and a fluid dynamically created pressure. And how is this wing section of a ram air wing here deforming under load? This effect is called ballooning because these would be the ribs made of fabric of your mattress. And in between the fabric can bulge out, and by that destroying the aerodynamic profile, which decreases the lift capability. We also do finite element simulations of complete kites, and you can imagine this is already quite complex model. This is a study we did together with Makani on the aeroelastic deformation of the wing. So you see one wing half, so this is the fuselage. Here the wing goes out. Here is an attachment point of the Y-shaped tether, and you see a very interesting effect that this tethering holds the wing down here. So you have this kind of inflection point here. So here is the free end of the wing. You see it also in this picture. Here we use vortex lattice method, or lifting line method actually, to simulate the aerodynamic load on this flexible beam model. This is a study we do together with Enerkite to study different layouts of the bridle line system. You remember this V-shaped wing is it's not a rigid wing, although it's a rigid structure, but the wing itself under load will become very flexible because it uses fabric as a canopy also. And the arrangement of these bridle lines is crucial to limit the deformation of the wing. Then flight control, the other big issue. We saw the night flight shot of kite power. This is a study of my PhD researcher on the control algorithm, and here a nice movie of a pumping cycle. And I think it's either the kite mill or plane or MPX Power. He collaborated already with both of you, Sebastian Rupp. Sebastian, who did that simulation, is a researcher in our Westwood Doctoral Training Network. Kite mill and MPX Power were partners in that network, and we had an active exchange of students so they can get industry practice. And one of these practices to develop flight controls. See how the kite, the plane moves up and then goes again into pumping cycles. Kite park layout is another active field of research. Most of the companies are not there yet, but that will come soon. Because we have done that on a simulation base, going from one kite to 4x4 kites to 8x4, and shift the pumping cycles, you can equalize the power output of the entire kite park. So when one system is reeled in, a few others are reeling out and can balance that energy consumption. So you can reduce the total storage capacity that you need in a park. And that simulation nicely shows that with a larger array of kite power systems, your battery storage is only required to start up the system in the beginning. Safe and reliable operation. I put this plot here from 2012. This was happening during a launch when the tether ruptured accidentally. You see here these fragments are from the ripcord shock damper. And then you see how the kite here lands safely. Unintentional Yeah, but we wanted to study that. And this is one of the most recent attempts to bring industry and academia together. We develop a reference system for an airborne wind energy system in the megawatt class together with the simulation code that is all available open source, or will be available open source in a few months. We took as an example the AP4 of Ampix Power, of which we received only the wing surface area. That's the only actual knowledge that is in that plane. Just to have a model with all details about the airfoil shape along the wingspan, the dimensions, the mass distribution, the aerodynamic coefficients of the plane, the simulation software, the control software, that will all be available for research groups and industry to actually access and use and do benchmark comparisons against. The model that we have in mind is the NREL 5 megawatt wind turbine, only now for airborne wind energy systems. I think the best is if I stop here and go to the last slide, which is and because then you can also ask questions.